Hi, my name is Jorge Figueras Toro and I will be presenting phase C1 of Functional Finger Prosthetic Designs, the subsystem control. In the outline we have the interface diagram, detailed analysis and design studies, design to specifications and drawings, verification and project plan. We have the interface diagram from phase B, a one-hand prosthesis that is modified with a myoelectrical system and a motor so that if a person is using the one-hand prosthesis, assuming that the prosthesis has full charge and all the components in perfect conditions, want to control it, they can do it so quickly, safely, and efficiently. For this, we have to know the following data. Here in the right, we have the model of the 3D model of the hand prosthesis modified with the myoelectrical system with the motor, the processor and the sensor, and in this design the cables are not included. Okay. Now the questions of the interface diagram with the detailed analysis and design studies. Where is the best place or area to put the sensor to have best control of the prosthesis? Position and orientation of the muscle sensor electrodes is very important. After studies, the best area to put the sensor in order to control the prosthesis is the forearm in the flexor pronator muscles or directly in the bicep muscles, always in the center of the muscle. Question is how much construction does the user have to do to send the signal to the myoelectrical sensor? After a study, the best signals are typically produced in a range of effort between 10% and 40% of maximum voluntary construction. The next question is how long does it take to learn to control a myoelectrical hand? We have three phases. The signal training, that is the first phase of training, teaches the amputee to control the muscle required to operate the myoelectrical hand. The second phase is the control training, at which time an amputee learns to control the muscle appropriately to perform a required function. The third phase is functional training, and it is important that the artificial hand fits correctly before beginning of this phase of training. Functional training is the most intensive phase of training and can take between 2 weeks and 2 months. It may vary for children. The takeaway is that we have three phases of training. Training is an important factor when an amputee has been fitted with a myoelectrical hand. It helps the amputee incorporate the artificial hand into his life, and the amputee learns what the prosthesis can actually do for him. Is how does the control components of the prosthesis should be connected for the user to control the prosthesis. In order to work correctly, the controls component of the prosthesis should be connected as follows. We have a recommendation that is demonstrated in the left, but I did a circuit diagram with the Arduino processor connected to the sensor, the two servo motors connected to the battery. The wire connected to the motors will be 4 principal fingers connected to one servo motor and the thumb connected to the other servo motor. The next question is how the processor sends the signal to the motor to start to run for the finger to be completely closed and turn off the engine for the finger to reopen. The Arduino processor should be programmed using a code like this. This is a prototype code that we will be using in the prototype or the simulation of our prosthesis. The design to specification and drawings, we have the tail on hand and the part list with the fingers, the pinky, the thumb, the palm, the small pins, the forearm, a sleeve, the sensor case, and the wrist joint. Here we have the other part of the design and specification and drawings. We have here the component case, and the part list is the component case, the lead, the sensor case, the servo motors, the Arduino, and the battery case. Here we have specifications of the sensor. We have the electrical specifications, the dimensions, and the sensor layout. Verification. Here we have the MOPs of the electrical motorized control system. The sensor electrode must fit on a 5 to 6 cm diameter of skin. This was met in phase C1. Sensor electrode should captivate 100 mV action potential. This was met in phase B. The components we choose met this according to the details of the manufacturer. Circuit should be reliable to send 5 volts DC to the motor. This is met in phase C1. Microcontroller must work with 0 to 5 voltage input-output. This was met in phase B. Torque of the servo motor should be greater than 100. This was met in phase B. Should have long use batteries, at least 8 hours of daily use. This was met in phase C1 with the use of the batteries. Must have good wire connection to send 100 mV efficiently at the circuit. This was met in phase C1 with the design of the circuit diagram. Verification budget. We have the components that the prosthesis, the motor, the processor, the sensor, the flexible nylon paracord to pull the fingers back, and the batteries. The takeaway is that the total cost of the control system is 156, that is on budget is less than 250. And finally, we have the project plan that we will be presenting the phase C2 on February 10 of this year. Thank you.